This is Newton's second and third laws, which are chapters 3 and 4 in your book, and this specifically is the first part of a two-part mini-series of videos. So this is Newton's second law, and then when you're done with it, please watch the video on Newton's third law. Newton's second law, as you know, is force equals mass times acceleration, and in science we actually refer to it as F equals ma, and so that's where the line in the chant comes from. F equals ma is what it's all about, or whatever that line is. And so if you notice, the unit for force is the Newton, the unit for mass when we're talking about Newton's second law is the kilogram, and the unit for acceleration is meters per second squared. So if you multiply a kilogram times meters per second squared, you get a kilogram meter per second squared. And if you go back to our force notes earlier this year, you'll see that that's how I defined Newton originally. So now you can see how that's kind of all coming together. And there's two ways that we can really use Newton's law. Newton's second law. The first way is in direct calculation. If you have any two of these quantities, so any two of force, mass, and acceleration, then you can calculate the third. And you may need to do a little bit of easy algebra where you rearrange the equation to get the third quantity, like you would solve for x in math, but here you're solving for mass or solving for acceleration. It's the exact same process. Or if you have mass and acceleration, then you can solve for force. So let's just do an easy example of that. So for example, how much force does it take to accelerate a 2-ton car by 2 meters per second squared? So go ahead and pause the video and then see if you can figure that out, remembering that the unit for mass is a kilogram, not a ton. So you might need to look up how to convert tons to kilograms, or hopefully you can figure that out yourself. So step one would be to convert tons to kilograms to make sure you have the correct conversion. So we start with 2 tons. So 1 ton is 2,000 pounds. So we set it up in this way, and then your tons cancel. And then 1 kilogram is 2.2 pounds. So here your pounds cancel, and you end up with 1,818 kilograms. And then all you need to do is substitute that into your M and your A in Newton's second law to calculate force. So force equals ma, which means force equals 1,818 kilograms times 2 meters per second squared, which means the force here is 3,636 newtons, which is a kilogram meter per second squared. And this equation then can be used to help us understand some of the stuff we've been taking for granted. For example, we've talked about how your weight is when you multiply your mass times gravity. Well, mass is m, and when we say gravity as 9.8, for example, here on Earth, we're actually talking about the acceleration from gravity, how much things that are falling accelerate by, and that's 9.8 meters per second squared. So again, you're multiplying your kilograms multiplied by meters per second squared, and that gives you a force. That force is called weight. And remember, we talked about that an object's weight is actually a force. Another place where we see this being applied is we've talked a lot about objects in equilibrium. Well, objects in equilibrium, remember, are not accelerating. Their acceleration is 0. So 0 times any kind of mass is going to give a force, or in this case a net force, of 0. Meaning objects don't need a force on them to remain in equilibrium, whether they are moving or not moving. So those two things together, or these two examples, kind of become a little more clear when we start to understand Newton's second law. The second thing, though, that we can use Newton's second law for is to really help us understand the relationship between force, mass, and acceleration, just like the song says. And by that I mean, see how these influence one another in more than just calculating a third quantity. So For example, in the bumpiness lab, we saw that the greater the frictional force, the more slowing there was, and slowing being negative acceleration. And if you're wondering where that negative is coming in, a frictional force is actually a backwards force. So technically on a force vector diagram, you would label it as negative. The negative here referring to direction, not to magnitude. We've seen that a couple of times, like in velocity. So the greater frictional force you had, the bigger your F was, the mass stayed the same, the bigger your A was, meaning you had more negative acceleration, more slowing. There are two terms that really help us understand or describe this relationship. The first term is inversely proportional, meaning when one thing goes up, it causes another thing to go down, and vice versa. So getting outside of the realm of science, you could say the more pizzas you order, as that increases, the less money you have in your bank account. The money saved decreases. These are inversely proportional. So when one thing goes up, it causes another thing to go down, or when one thing goes down, it causes another thing to go up. We also use directly proportional, meaning when one thing goes up, it causes another thing to go up. So as I increase the number of pizzas I eat, my mass or weight, because here I am on Earth, increases. Those two go up together. Or if one thing goes down, it causes another thing to go down. If I now go on a diet and decrease the number of pizzas I eat, that causes my weight to go down, assuming, of course, I don't replace it with Snickers bars. So, two examples, mass and acceleration are inversely proportional. When mass goes up, its acceleration goes down, assuming you're using the same force. So, if you push a tennis ball with a force of 1 Newton, it accelerates some certain amount. And we could calculate that amount if we knew how many kilograms the tennis ball weighed. We don't really care in this sense because we're simply looking at a relationship. If you then were to push a tennis ball filled with lead, which obviously has more mass, with a force of 1 Newton, so the same force, it doesn't accelerate as much. The acceleration has gone down as the mass went up. Another example of that is that force and mass are directly proportional. When mass goes up, so does the force needed to accelerate it. So, let's go back to the above example. If you want the lead-filled tennis ball to accelerate the same amount as the regular one, so now you're going to get the same acceleration, you would need to use a greater force, because the greater mass requires a greater force. Those two are directly proportional. Going back up to the bumpiness lab, where we said the greater the frictional force, the more slowing or the more negative acceleration you have, would that make force and acceleration inversely proportional or directly proportional? Think about that one. Pause the video, write down your answer. So you should have said directly proportional, that the greater the force, the greater the acceleration. Or, similarly, if you want a greater acceleration, you need to use more force. So those could go either way. One could cause the other. So now, this is sort of the end of Newton's second law and a good stopping point in the video. You can go ahead and ask questions, type in comments if you have things specifically about this one, or you can hold on to them until you've listened to the third law video. But either way, go ahead and listen to the third law video.